With hypothesis testing, it's very important that you set it up with the right hypothesis at first, so you can prove the thing that you want to prove. Or in particular, the statement that you want to prove is true needs to be the alternative hypothesis. That way, by showing that the null hypothesis is most likely false, then you show that the alternative is true. Here's an example. Example is concrete pillars. So someone was just telling me about this. At Sac State, they have a press, so they make these reinforced concrete pillars here, and then they put them in a press that exerts all this force up and down, and they do it until they're completely smashed. So they smash them. So the force it takes to smash them is how much it can support, right? How much weight it can support. Well, suppose you want to show that this particular pillar supports at least 10,000 pounds. So if we look at it this way, you want to say that mu is greater than 10,000. That is, the mean weight before failure is at least 10,000. It's also important to know that we're talking about the mean. So in this application, the standard deviation always matters, because in particular you want all the pillars to support at least 10,000 pounds. So that's why there's large margins of safety with all these things that are bearing weight and potentially catastrophic failures. So this should be your H1. So working backwards from there, you want your H naught, your null hypothesis, to be that mu is less than or equal to 10,000 pounds. So in this way, we kind of work backwards to get what we want. So then you do your experiments, you crush a bunch of pillars, and hopefully you can show what you intended to show. But if you can't, you've still learned something, right? You can still draw confidence intervals about how much it supports and that sort of thing. So even if you didn't get your original goal. Another thing to say on the subject of interpreting hypothesis tests is that statistical significance does not imply practical significance. That is, something can be statistically significant. So significance here, it has a technical meaning in statistics, right? It's this kind of interpretation. Your p-value is small, so you say it's statistically significant at the 2% level for this. If you get your value, p-value is 0.02. That is the technical meaning and usage of statistically significant. People get confused, though, because they hear the word significance and they think it means the same thing that we use in common everyday English usage, which is typically practical significance. But they are not the same. So here's an example. You have a new miracle diet program comes out. And on average, people lose, say, 1 pound of weight. So this could be very statistically significant. You could get a bunch of people, put them all on the miracle diet, and find out that they lose 1 pound. But practically, this isn't a significant enough difference for people who are looking to lose weight by changing their diet. So this is relatively small, and that is not practically significant. The other thing to realize about statistical significance is that x bar is distributed as normal mu sigma squared over n, where this n here is the number of observations. So increasing n means it's more likely to be statistically significant. That is, if you have a very large n, you can detect very small effect sizes. But these small effect sizes, that is like 1 pound of body weight on a diet, is a small effect size. These small effect sizes are unlikely to have practical significance. So that is, the more data you have, the more likely you are to get a statistically significant result that's not practically significant.